Yeah, then good morning everyone, and thank you very much for giving me the opportunity to share some thoughts with you regarding how safety is and will be affecting our work lives as engineers who develop products for the automotive microcontroller market. Try to switch. Yeah. In recent years, safety applications have already become very common for modern cars. They contain up to 100 or even more ECUs. And on this slide, you see a selection of safety applications which are supported by the Infineon Oryx product family. The Oryx architecture, I don't know whether you see my mouse pointer. This Oryx architecture has been developed according to an audited ISO 26262 compliant process, and it meets the ASIL D on an application level. The Oryx platform integrates, you see, up to 3 tri-core CPUs and has extra 2 cores in the tri-core diverse lockstep core technology, which also has a clock delay, so clock cycles, 2 clock cycles delay. The cores operate at up to 300 megahertz clock frequency and offer up to 8 megabyte of embedded flash at the high end. Additional safety technology comprises safe internal communication buses or distributed memory protection systems. New encapsulation techniques allow the integration of software with various safety levels, which are QM, which is just functional quality level, to ASIL A until ASIL D, so the automotive safety integrity level classification. Multiple applications and operating systems, which are, for instance, steering. I'll show you some examples. Steering applications, braking systems, airbag, and also advanced driver assistance systems with multiple purpose camera configuration and or radar system included. They are supported by one unified platform. This device also includes high-speed interfaces, integrated hardware acceleration, and enhanced ECU validation and instrumentation tools. As all the ADAS devices have been designed in accordance with the ISO 26262 safety standard, they are allowed to take automatic decisions to assist drivers, for instance, for emergency braking. So, of course, this is the current product family, and we are already developing the next families. They will have even more automatic driver assistant features, so the safety will become much more important, as it is already today. The ISO 262 standard defines rules for electrical and electronic systems at item level in mass-produced passenger road vehicles up to 3.5 tons. Its goal is to help achieving the absence of unreasonable risk to the health of passengers due to hazards caused by malfunction behavior of EE systems within the car. The standard specifies safety requirements covering the complete life cycle, including functional safety management, concept, product development at system, hardware and software level, production, service and maintenance until decommissioning of the product. Thus, not only the product has to implement a wide range of safety measures, which are typically based on redundancy, provide mechanisms for error detection and correction, alarm generation, and handling of alarms in order to achieve a safe state. They also may include self-test mechanisms in order to ensure that the installed safety measure is still alive. Moreover, the complete development flow must be compliant to the ISO standard. So not just the product itself, but also the design flow. There are about 130 safety work products of the standard, which include guidelines how to do the work, include templates for the required documentation and checklists to confirm that the safety requirements have been really fulfilled. For each work product, confirmation measures such as confirmation reviews, safety process audits, and functional safety assessments need to be carried out in order to provide evidence that the safety process has been properly completed. Based on the assessment of the violation of safety goals, the classification into 4 possible automotive safety integrity levels ASIL A to D is done. All this not only sounds like a lot of additional work to be done on top of the actual development effort, it actually absorbs significant engineering resources. So as a consequence, products become even more complex due to the additional safety measures. The power consumption will be higher, the area larger, which directly translates into increased production costs, and many more person years must be spent. This causes a real dilemma. On the one hand, there's no chance to place the product in the market without having the ISO 262 certification. On the other hand, it might turn out that the product is very expensive or is more expensive than without all these measures and certifications. So the question is whether markets are really able and willing to pay higher prices for products which actually cost more in their development. So the question is how to get out of this dilemma. The answer is that we need very smart tools and very smart methodologies which help us to reduce the cost of this extra development and the extra measures to be taken. Now let us take a look at a few specific challenges. Of course, the ultimate goal here should not be just to get the product certified to be ISO compliant at minimum costs, but also to offer automotive microcontrollers which truly avoid harm to human beings caused by malfunction. So the first challenge or question is, who knows what really can and needs to be done for maximum safety? Because safety is far from being an exact science. Different safety experts tend to have diverging opinions, especially when it comes to details, what to do or not to do. The problem is only if an initial approach is revised, after a lot of effort has already been spent in one direction, the overall cost of the product development can become higher than if the right decision had been taken upfront. Safety requirements may be very different in different markets. For instance, what is understood by unreasonable risk? Driving a 300 horsepower BMW on a German motorway at a speed of 210 kilometers per hour clearly makes a difference to using a Chinese highway during rush hour time where 8 cars side by side without marked lanes keep a distance of less than 1 centimeter to each other. Or where, as it sometimes happens, the covers of canalization funnels in the middle of the road may have been stolen overnight because of attractive steel prices. I really experienced this when a taxi took me from Xi'an airport to the city. Fortunately, the taxi driver already knew about this premature recycling habit practiced in this region and took the safety measure to slow down his car just in time to be able to circumvent this dangerous zone. An ADAS system with even 8 radar antennas or 8 cameras would probably not have detected this anomaly on the highway. So it seems that the safety requirements of markets in countries with the highest growth rates are lower than in the saturated developed economies. On the other hand, the demographic situation in the developed countries gives rise to the expectation that there are true potentials for automatic driver assistance systems. The standard obliges the supplier of the safety product to implement the state-of-the-art. However, as the state-of-the-art is permanently progressing, a specific approach may be outdated after a few years. Moreover, for the products developed today with shrinked chip technology and completely new features which will be used in future cars in several years, no experience and no field data with actual failure rates is available yet. Therefore, the safety decisions are based on assumptions and estimates. It may well happen that evaluations of measurements collected during operation will give rise to modifications of safety mechanisms if they should turn out to be insufficient or also superfluous. For example, if a specific alarm has never been raised. The next question is how to master the increased design flow complexity. Application of the standard clearly causes such a proliferation of documents that tools and methodologies which support the extra documentation and the requirement tracing work should help to minimize the part of the overall safety effort needed for managing the huge amount of data to be generated, reviewed, maintained, and assessed. Various metrics for assessing the safety level, the quality of design, and progress must be supported by the tools. For assessing the fulfillment of the required ASIL, we need to provide diagnostic coverage figures in order to give evidence that the percentage of faults not controlled by a safety mechanism is sufficiently low for the required automotive safety integrity level. Such figures are typically generated by fault simulation. Here, formal verification can greatly help to prove exhaustively that the specific safety mechanism actually covers all elementary parts of a component. An example is, for instance, ECC, which covers then all 1-bit errors in data stored in a RAM. Verification tools already provide coverage data for functional verification, which needs to be automatically included in the safety flow. So all this must be done and supported by advanced tools which support the flow. What are the prospects for the future? It is very likely that even more safety will have to be installed in future cars if more and more functions, which are today still in the driver's responsibility, will be automated. The question whether the end user is willing to use and pay all these nice-to-have features and give up more and more of his independence is a different topic, maybe especially in Germany. And whether he will have the choice at all, like smartphone users cannot prevent top companies collecting lots of their personal data. If you look at the risk analysis by which ASIL classification is done, it depends on 3 factors. Severity, the harm to people caused by the violation of a safety goal, which may range from no injury to fatal injury. Second, the frequency of the occurrence of a hazardous event, which is a product of the probability of exposure to the hazardous event and the failure rate that could lead to the hazardous event. And finally, controllability. This is the chance for the driver who is part of the safety system, like the taxi driver in Xi'an, to control the hazardous event. High exposure and severity combined with low controllability results in the highest ASIL D classification. If now, in future, not just drive assistance systems, but fully automatic autopilot systems will be installed in cars, the driver's controllability is reduced to a negligible minimum. Naturally, the average ASIL classification will become much higher, and accordingly, the importance of automatic safety mechanism. It might also happen to the extreme that based on the evaluation of field data, regular safety patches must be provided by the suppliers, in a similar way as Windows computers have to install software updates several times in a week in the meantime, or virus software needs permanently to be updated with new virus definitions. Of course, security is another key issue for the future, which is very closely coupled with safety, since hackers could not only collect confidential data in this case, but take control over safety-critical function. For all these reasons, it is very likely that current safety methodologies will have to be significantly augmented in the next years. With regards to the competition, the question is how many players will be able to handle the additional complexities and still be profitable. Technically brilliant innovations will not be sufficient to survive, but the best development methodology will play a key role by addressing real needs, flexibly reacting and changing requirements, and using tools which really support the engineers rather than constraining them to the capabilities of the tools. So let me now come to an end with some conclusive remarks. So less driver control means that ultimate reliability of ADAS and autopilot systems is required. Then safety, robustness, and more security are key success factors of future automotive products with the evolution of even more sophisticated functional features. Safety development must still be payable, otherwise the market will simply not adapt this. We have examples of this where interesting technology was not adopted. Therefore, advanced tooling is needed for supporting the development flow and keeping the development costs manageable. Metrics and formal compliance with standards supported by such tools are very important. At the same time, the underlying technical contents, which can only be based on human engineering capabilities and judgments, will remain even more important. With this final remark, I would like to close my talk and thank you for your attention.
Okay, thank you very much, Holger.
So are there any questions?
I can't see any questions online at the moment. Oh, sorry, there are a few questions. So, one question from Jason McAllister, will the session be recorded? Yes, we are recording the session, and we will be sending you a link to those. Okay. A number of people were saying we were stuck on slide 3. Holger only had 3 slides, so everyone was stuck on slide 3. Maybe we should have explained that in advance, Holger. But yeah, Holger only had 3 slides. So I can't see any technical questions for you at the moment, Holger. It was more admin questions. So to answer your admin questions for everybody, the presentations will be made available afterwards. Everybody was on slide 3 because Holger only had 3 slides. Okay, so just remains for me to say thank you very much, Holger. Thank you very much for your time, and thank you very much for your presentation.